Hello and welcome to Disseminate, the Computer Science Research Podcast. I'm your host, Jack Wardby. I'm delighted to say I'm joined today by George Theodorakis, who will be talking about his VLDB 22 paper, Scabbard, Single Node Fault-Tolerant Stream Processing. George was a PhD student in the Large Scale Distributed Systems group at Imperial College London, and he recently submitted his thesis. And he also recently joined Neo4j in their research lab. George's research interests lie in the areas of distributed and parallel computing, database management systems, and stream processing engines. George, thanks for joining us on the show.
Thanks for having me. It's interesting to discuss about our latest work on stream processing.
Brilliant, let's dive straight in then.
Yeah.
Can you start off by explaining to the listeners what stream processing is and what its common use cases are?
All right, cool. So in the last years, we've seen an explosive growth of data volumes and velocity, and at the same time we've seen the emergence of kind of a new type of applications that are long running. These applications run for hours, for months, for days, for even years, if you can make them work that way, and execute continuously. So they execute as new data arrives. And this data can be possibly in the form of infinite streams, right? So you have to deal with the problem of data that are infinite. You don't know their size in advance. So pretty much this stream processing, it's the processing paradigm that allows you to process real-time data that are infinite. According to estimates, we expect 30% of the data in the future to be produced and analyzed in real time. And this makes stream processing a paradigm that is established between transactional processing, online analytics, and reporting. Some common applications for stream processing are high-frequency trading, card fraud detection, sensor monitoring. And the common characteristic of these applications is that apart from having to deal with very high throughput of data, you also have to report in sub-second latency. You have this requirement where you have to respond very fast, and whenever you delay your responses, you have adverse effects. So, for example, in the case of health monitoring, you have to respond within seconds, right, in order to matter. Or in the case of high frequency trading, you have to, the significance of your results decays with over time. So you have to respond as fast as possible to make more profit.
Awesome. So how did you end up researching in this area?
I'm 6 years ago, I was trying to find a topic for my undergrad thesis, and it happened that I worked with some people from Imperial College London at the time. So they just had published their stream processing engine, and we wanted to collaborate with them. So I worked with a system they had back at the time, trying to do stream query optimization at the logical and physical level. And they use Apache Kafka, which is an extensible data management framework.
Okay. Nice.
So we worked on how we parse stream queries, how we optimize them. And at that time, there was also this hype with Apache Flink, Spark, and Kafka. So I decided it would be cool to work in the field. Also, one of the reasons that I chose the field was that back at the time, it wasn't that mature.
Right, yeah.
So there was a lot of space to experiment and try things that people haven't tried.
Cool. So let's dive into the paper then. Can you tell us what is Scabbard? And am I pronouncing it right?
Yeah. So Scabbard is like a holster for your sword, right?
Okay,
something to protect your weapons. We have this thing that we name our projects after weapons.
Okay.
The initial project was Saber, then its extension was Lightsaber, and then Scabbard is the one that protects the lightsaber. Anyway, so we had this single node engine, this single node system that ran efficiently on multi-core systems. And we wanted to make it fault tolerant. So this means let's step back. For the context, fault tolerance means that we have to be able to handle failures, because we are running our software in either local clusters or on the cloud. There are cases where things can fail, either because of bugs or because the node crashed, right? So you have to be able to handle failures and hide their effects completely. And we try to design a system that can achieve this in a single node, which is kind of counterintuitive, given how people are doing this.
You mentioned earlier on systems like Apache Flink and whatnot. So they're distributed stream processing engines, and this is a single node stream processing engine. Can you explain what the differences are between these two systems?
Yeah. Systems like Apache Spark or Flink adopt a shared nothing execution model. And their whole design allows you to parallelize your computations to many nodes. You get, not for free, but easier features like fault tolerance. They have very nice APIs. They are mature. You can do many stuff with them. But because of their design, they face many challenges. The first challenge they face is that because we are now doing computations over the network, we have to pay the price, right? So we have cross-process and network communication overheads. We have to serialize our data. We have to design our data structures and our algorithms with a different way. We don't have shared memory. So we increase our resource and maintenance footprint, definitely. So this is one challenge. The second challenge is that because we are over the network, we cannot really have predictable performance guarantees. So earlier I mentioned that mainstream processing applications require very low latency, and this cannot be, you cannot guarantee this when you do processing over the network, when you try to scale very high throughput streams. And one third issue is that many parallel computations, many operators are very hard to parallelize efficiently in a distributed environment. For example, aggregations with windows. So windows is a form of a structure that allows you to process this infinite data. So in the case, for example, of window aggregations over windows, when you do them in parallel in a distributed environment, you have to either perform redundant computations or you have to approximate your window results because you don't have a global clock in a distributed environment. I think the most important bit is that you have to pay the tax of distributed execution.
Yeah, it reminds me of the cost paper, right?
Yeah, it inspired us a lot for our project. So yeah, and at the same time, you see that there's this rise of shared multi-core CPUs, where you have many CPUs, many sockets, and you have terabytes of memory. You have accelerators like GPUs, FPGAs, so you can do a lot of stuff with a single node, right? You can optimize for latency, you can optimize for throughput, you can redesign your algorithms, your data structures, and also now with the high-speed networking that's been enabled by RDMA, remote direct memory access, you can ingest a lot of data and you can even perform fast storage to remote disks. So a single node can handle a lot, and usually from most of the use cases we've seen where you have to handle hundreds of gigabytes of data, you can fit them in a single node. So it's possible to have this as an alternative.
Okay, cool. So you kind of summarized in your last answer there what the advantages of these single node stream processing engines are. But what are the significant sort of downsides, what are the pitfalls, and that have maybe limited the adoption of single node stream processing engines in practice?
What I forgot to mention before is that with single node implementations that we've seen mostly from academia, you get usually at least an order of magnitude better performance in terms of throughput and latency. So this is the benefit that you get when you don't have the tax of distributed execution. So, I mean, these are nice, but nobody really uses these systems in practice. And that's mainly, we think that happens mainly because they lack fault tolerance mechanisms. As I said earlier, when you run continuously and long-running applications, there's a higher chance that your node is going to fail and you have to restart and produce correct results. For many applications that it really matters. I think that one of the biggest drawbacks is that these systems don't have built-in fault tolerance mechanisms. And while the strawman solution would be to just take the approaches from distributed execution and plug them into single node, this would end up blowing up again your cluster size, right? Because you will need many nodes to perform persistence, many nodes to, I mean, the way they're implemented right now, many nodes to perform persistence or recovery or the bits that are part of the fault tolerance mechanisms. So in the paper, we had this interesting experiment where we're using a single node system. And so this system could ingest like tens of gigabytes of data per second, right? And in order to make it fault tolerant, the simplest solution would be to use something like Apache Kafka to persist our input streams so that we can replay them when they fail. And we noticed that for such use cases, we would need like a cluster of at least 20 Kafka nodes to persist the data streams that we needed. So yeah, it kind of comes back to the efficiency argument, right? And yeah, but if you have a single node and then you need 20 Kafka nodes, you end up in a distributed environment again. So
back to square one. Right?
Yeah.
So yeah, cool. So kind of, I guess, yeah, building off that, what were the design goals that you had in mind when you were developing Scabbard?
So we already had a system that had very high throughput and low latency.
Yeah, maybe you could mention the previous, because you mentioned earlier on the journey from sort of, what was the first one?
The first one was called Sabre.
Then Lightsaber, then Scabbard, right? That's the flow. So yeah, maybe we can talk about those.
Yes, I didn't work with Sabre. I mean, I didn't work on that paper. So Sabre was like the first step that was trying to utilize a single node with GPUs.
Okay.
And do this. It was designed to like schedule tasks on both CPUs and GPUs and run them in parallel. And Lightsaber was kind of the next step, an optimized version of Sabre, trying to use NUMA-aware execution, simple instructions, code generation. So we had like this system, this efficient multi-core system. There are many similar to that, right? It wasn't just this one. And we just wanted to so we already had high throughput and low latency. We just want to ensure that we can still have these performance guarantees during the execution that doesn't have failures, which is like the common case, right? So whenever we didn't have failures, we just want to ensure that we have these requirements. And the second design goal had to do with the limitation that we have to deal with in a single node. So when you're in a single node, you have limited resources in terms of network and disk bandwidth. So you have to be careful of how you use these resources and which data you choose to store and which data you choose to like zip over the network. So yeah, our second design goal was to deal with these limitations. And the third goal was to guarantee fast recovery because we are in a single node environment. Of course, we don't have high availability, but we have to, because we have a single point of failure, we have to provide sub-second recovery so that we decrease the downtime of the system when it's running. So yeah, I have performance guarantees, deal with the limited resources of a single node, and guarantee fast recovery. That was the key goals.
Cool. So I guess, how did you go about addressing these design goals? What's the key idea underpinning Scabbard? And let's start with that, and then we can dive into. I know in the paper you said there's 3 main contributions, and we can talk about those in a second. But yeah, what's the kind of key idea that you had to address these design goals?
So when we're trying to implement the system, a step back, which is something I haven't mentioned properly. When you're in a streaming world, in order to achieve fault tolerance, you have to persist at least all your input streams so that you can replay them and catch the correct recovery state. And as an optimization, you can always checkpoint your operator state so that you can cut down from your input streams. Now, in our context, in a single node execution, you were ingesting streams in the order of gigabytes per second, and also your state would reach the same magnitude, right? So you would have to persist per second tens of gigabytes, right? And this would have to happen with SSD disks, simple disks that have a bandwidth lower than gigabyte probably. So like commodity disks that you can find. And you already see that there's a bottleneck there, right? You cannot like store all of this data with a single SSD, right? And while you don't have this problem with distributed execution because everything is partitioned, everything works fine in a single node, that was our key issue, right? So the idea that we try to, the main idea behind Scabbard is that you have to reduce what you store to disk in order to accelerate fault tolerance. And you have to do it in a manner that is, that adapts to different workloads. So it has to be adaptive to different workloads so that you can get the best performance possible.
Cool. So let's go through the main aspects to achieving this. And so the first thing you mentioned in the paper is this idea of a persistent operator graph model. Can you tell us more about that?
Yeah, for our first contribution, we wanted to come up with a model that allows us to have the right abstractions to perform persistence and fault tolerance in a single node. So we wanted to integrate the persistence with the query execution so that we perform a series of optimizations. What this really means that we have encoded persistence as an operation in our data flow graph, execution data flow, and therefore we can reorder persistence as you would reorder, for example, a filter or a projection, and we can apply it after we have discarded data with highly selective operators. So we can, for example, when we try to persist our input stream, we can persist it after we have applied filters, projections, or we have applied compression, for example. That I will discuss next. And we can also identify opportunities where we can even inject operators like projections so that we can reduce what we store to disk. Yeah, we have this set of optimizations, and then we have the abstractions that allow us to efficiently persist both the data streams and the operator state that I mentioned earlier that we want to persist. And we also have some abstractions that allow us to coordinate all these operations. And based on all of these abstractions, like the coordination abstractions and the persistent abstractions, we built a protocol that allows us to provide exactly one's output. Now, what this means that we can, in the event of failure, we can hide completely its effects and provide the exact same results as if nothing happens. And yeah, I mean, this model tries to capture only the essential information that you need to persist disk so that you can recover with exactly one's output.
Okay, cool. So once we have this model, then the next component of Scabbard is this query-specific adaptive compression.
Yes.
How does this work?
So I mean, after doing the optimization from before, where you discard data and you pick what you're going to store from your streams and your operator state, we found out that disk was still the bottleneck, right? So the most natural thing to go after then was compression. So we decided to compress whatever was left to be stored for disk, what was essential for us to store to disk. And we decided to go for adaptive compression. Now, because as I mentioned earlier, we have to deal with long-running applications, we also have to deal with changing data characteristics. So it was essential for us to capture these changes by collecting lightweight statistics at runtime and choosing the most suitable compression algorithm based on these statistics. Because our initial system was using code generation for all the other operations, we decided to use also code generation so that we can reduce the overheads when you inject new compression schemes into the operator graph. And yeah, this is how the adaptive compression bit comes from.
Cool. So what sort of statistics do you gather? And
I mean, it's very simple. It's about the data distribution. So for example, we gather minimum, maximum values at runtime, or we gather, for example, try to use run length encoding if it makes sense. So we gather how many consecutive values are equal. Yeah. Statistics like this. So yeah, it's very basic statistics, but still they help us to identify which algorithms to choose. And sorry, one last bit that we collect that we measure is the bit precision for integers, and this allows us to pick the right algorithm to compress integers even better.
Cool. I was going to ask, how does these statistics then map to the choice of algorithm you use, and kind of what algorithms are supported, and how what is better for what is kind of the...
we don't have the proper optimizer there. It's just like we have probably 2 or 3 different algorithms for different data types, for example, for integers, for floats, for... It's not actually a data type, but for timestamps we consider it as a data type. Or for strings. But the logic of how you choose different algorithms is very simple. So basically we had some... we did some analysis and we figure out which algorithm to choose depending on your bit precision, as I said before, how many sequences of equal values you have, and so on. So we just have a greedy approach of picking the right algorithm.
I guess it's maybe an area for future research.
Yeah,
cool. And I guess we've got the persistent operator graph model, the query-specific adaptive compression, and the last thing that is a big contribution in the paper is the efficient failure recovery mechanism. So can we dig into that a little bit?
And
how it fits in with everything else, I guess, right? Yeah.
Yes. Yeah. So it's the other two are kind of more conceptual contributions, so high level. This is kind of more an implementation one. So it's kind of the third contribution that you have to put in your paper just to submit it, I guess, in a way. As I said earlier, you have to recover fast, right? So we were trying to optimize this path of recovery. And when we spin the system, you have to generate code for different operations, for your compression, for your operators, and so on. And all these things take time. So we figure out that instead of going through all the optimization phases all over again, trying to generate the code, we could just store the binaries and then load them. So this saved us a lot of time. And we also optimized checkpoints so that we can perform them frequently without disrupting execution. And by performing frequent checkpoints, you kind of optimize for recovery. So you can recover without having to replay a lot of data. And finally, we have a garbage collection mechanism that deletes data that you don't want to load when you recover. So we try to minimize the amount of data overall that you load from disk and how much time it takes to spin up the system.
Cool. So I guess we mentioned implementation there. So let's talk about the implementation a little bit more. So there's this path between Sabre, Lightsaber, and Scabbard. How did you go about implementing Scabbard? Is it all in the same code base? How does it all fit together? How did you go about implementing it?
Okay, so we implemented Scabbard atop Lightsaber. So Lightsaber was written in C++, and we used its query execution engine, its compiler, and we extended them. For example, we extended the compiler of Lightsaber to generate additional types of tasks. So we generate tasks for persistence, for compression, for checkpointing, and we try to integrate everything as a task in our system. We also implemented some features regarding networking, like how we do data ingestion or how we send data using our DMA just to make it faster. So anyway, everything in the system is a task, like from networking to persistence to compression to how you execute the queries. And all these tasks are executed asynchronously. And this helps our system design because you can hide all the latencies from disk and network. And you can better utilize the underlying hardware. So everything is a task, everything can be executed by all the cores that we have. Every core in the system is a worker. And we also optimize for locality. So all the tasks, the workers that are closer to the data will try to execute the tasks. And only if they don't have work, they will fetch something from another circuit. So this was the way to integrate all our logic with Lightsaber, just like to make everything a task and have all the workers having all the workers pushing the state of the system forward.
Okay, cool. So is it? Can I use Lightsaber without Scabbard? Is it pluggable, or have they now forked and they're two independent systems, or can I turn it off and turn it on again? Or has it been a complete, obviously, refactor of the original system, so it's something different now?
So the only thing that you have to do is that you have to set some flags
Okay.
in your operators to make them fault tolerant,
Right.
or to your data streams. And then, I mean, yeah, the API is not clean at all, but you have to set, let's say, some flags, and you choose either whether to use Lightsaber or Scabbard.
Okay. So did Scabbard Lightsaber pre-Scabbard, as adding that code in, if I turn off the flags, is there any overhead there since you've added Scabbard in, or am I basically getting Lightsaber as a baseline and then I'm just kind of losing a bit of performance by adding Scabbard on?
So yeah, definitely I haven't engineered the code that well, but
no, don't say that. It's brilliantly engineered, I'm sure.
So yeah, it just if you don't set the flags, you just like follow the Lightsaber, let's say, code path, and that's it. You don't have any overhead.
Okay, so you get it like as it was. Okay, that's fine. Cool. So what was your approach to evaluating Scabbard, and what were the questions you were trying to answer?
Cool. Okay. So the first thing that we wanted to answer was whether, I mean, after doing all these optimizations, all these new abstractions and all these things in a single node, whether its performance was comparable or better to existing state-of-the-art solutions, like Apache Flink, for example, that is fault tolerant, right? And we wanted also to see what's the overhead that we added. I mean, you mentioned earlier the overhead. We want to see what's the overhead compared to a system that's efficient single node system and doesn't have fault tolerance. So this is the first part, like our end-to-end experiment in terms of fault tolerance to see its overhead and how it compares to state-of-the-art approaches. And the second question that we want to answer was whether our approach of persisting data, like data streams, was comparable or better to an approach like the one used by Apache Kafka. So yeah, Apache Kafka is like this distributed messaging queue that people use to persist their data streams. So I want to compare with that.
What was the experimental setup? And you mentioned there what you compared Scabbard against, but yeah, what are the results? So by setup, do you mean like the workloads and where we run experiments? What the experiments you ran basically. I can reframe it as that if you want. Like, what were the experiments you ran?
Okay, so I mean, in stream processing, you don't have benchmarks to use,
it's
like
not a TPCC for benchmark,
TPCH or TPCC or whatever. Sure. So people just like make up their own benchmarks, or they use some that are not really good. So yeah, we just like went with 10 different queries that capture different operations like filters, joins, aggregations, windows, and so on. And we in the paper we have results from both our local cluster, where we run experiments with RDMA, and also from AWS, where we run experiments using EBS for remote storage, because we also want to verify that it works with remote storage in case that you have a failure and you have to start up in a different node. So yeah, we just hijacked AWS hardware there. So yeah, I mean, for the first question, for the end-to-end experiments, we used Apache Flink, which is state-of-the-art, but it's a distributed Java-based system. And we also use Lightsaber just to see the overhead compared to a system that doesn't have fault tolerance at all. Now, compared to Apache Flink, we got at least an order of magnitude better results in terms of throughput and latency. And compared to Lightsaber, we saw on average a 30% performance degradation in terms of throughput, and close to 8 times, I think, if I remember correctly, worse latency, because we're adding in the path the disk. So the throughput was good, but yeah, you have to wait a little bit more for acknowledgements from the disk in order to continue with the processing in many cases.
Makes sense. Cool. Did you run any experiments to kind of measure how fast things recover? And did you compare this? Did you do like a recovery experiment to see how quickly things came back online if failures occurred?
I mean, I didn't
don't know what that test would look like even, but did you explore that?
Yes, I didn't try. I mean, we tried Flink, but the results were really bad, so we didn't include. Yeah, we didn't include the graph there. We kind of cheated in our recovery experiments. So, I mean, in order to have like a proper recovery solution, you should be able to have a module that can discover that you failed, which I guess it's the most expensive part, right? Because you are never sure whether you failed or not. And I guess you can do it with timeouts or something like this. I'm not sure.
There's some solution there, right?
Yeah. Anyway, so we skip that part and we just measure how fast we can recover from the point that we fail, assuming that we instantly know that we failed and we have to recover, right? And in that case, we had sub-second recovery latencies, which was, really good. As I said, we optimized for it because we just reloaded everything from this, like the binaries and all the code for compression and decompression was there, so you knew what to do. So that was an experiment for recovery. I mean, it wasn't an end-to-end experiment. It was kind of a micro benchmark, but
yeah. No, but it gives you a flavor of how it would perform in practice, right?
Yeah.
Which is good. So that's kind of obviously all the headline results of your experiments. But are there any situations in which Scabbard's performance was suboptimal? The question I'm kind of getting at here is, what are the general limitations of Scabbard?
It's an academic project, so it has many limitations, I guess. So first, in our exactly once protocol, we assume that the sink, so the sink is the receiver of the results, the sink participates in the protocol. So the sink we are sending to the sink some metadata that the receiver that would allow it to perform deduplication. So when you recover and you start sending again your results, you may send some duplicate results. And in our protocol, the receiver is responsible for dropping these results, which is a big assumption because it may not be able to handle this logic. So if it couldn't handle this logic, then we would have to end up with something like distributed transactions. And then we go back to distributed execution again, and it's the same issues. But maybe you can, so maybe a way you could do it is that you could offer it as a service, and you could have probably many Scabbard nodes for many users and handle distributed transactions in such an environment where you wouldn't have like the overhead of a single node having to deal with transactions. The second limitation is that we cannot deal with non-deterministic operators. So imagine that you have an operator, for example, that accesses some external database. We cannot definitely handle this, because in such case you will have to track down some additional metadata and replay. And when you do a replay, when you restart, you have to be sure that everything happens again as it happened earlier. So you have to track your history and track more metadata there. That would be an extension. And we also cannot handle out-of-order data. So what this means, so we assume that everything comes in order. So everything is, you would never find a tuple that has a late timestamp, okay? So your data is ordered by timestamp, and you assume that everything that comes is in order by the timestamps that you have, right? So if something comes out of order, it would break our execution engine. So Lightsaber was designed to be in order, and because we built on top of Lightsaber, we just didn't try to extend it towards that area. So to extend our system for out-of-order data, you would have to introduce some additional markers, some special tuples, okay? And these tuples would tell you how far you've reached in your data in terms of the timestamp. So it will tell you, for example, that you've seen all the data up to minute 10 or something. So you know that it's safe for you to do all the operations up to that point. These are I think the three most important limitations that we have.
Okay, cool. So is Scabbard publicly available? Can I go and get my hands on it and I can play around with it if I so please?
You can find like the link for the GitHub repo in the paper.
Cool. And we'll link it in the show notes as well, so
the
listener can go and find it.
Even better, you can find it. Yeah.
Cool. So I guess building on that theme, if I was to go and play with it and have a mess around with it, I know you said it's only an academic project, so it won't be as say usable as a commercial system, say. But what's my interactions with Scabbard look like? How do I go about writing applications on top of it?
As you said, it's an academic project, right? So I'm the only one who spent time writing code, and I'm probably one of the few people that have used it. So
not after this podcast, everyone will listen to it.
You go crazy.
It,
okay,
yeah,
cool.
yeah.
So I have to fix many things. So yeah, I mean, it has an imperative API. So you kind of like define your operators. You can define filters, projections, joins, aggregations, and you kind of chain them together so that you do so that you have pipeline parallelism. It's kind of similar of how you would create, for example, in Spark or Flink or Storm, your pipelines, but it's much more rough.
Okay, cool. But it bears resemblance to that, obviously.
Yeah.
Okay.
So yeah, I mean, we also have some. I mean, all the benchmarks. We've implemented all the benchmarks and we have the code in the repo, so you can find and use them as, let's say, your base to build something that looks like these applications.
So I guess my next question is, what was the most interesting, and I ask this to everyone, what's the most interesting and perhaps maybe unexpected lesson that you learned while working on Scabbard?
I mean, when we started the project, I was very pessimistic because I wouldn't expect to get good performance while persisting so many data on disk. So in a way, like having this like, I mean, it's not minor, but this small performance degradation while you store such an amount of data on disk was kind of unexpected. So yeah, that was like a really nice result of how you can multiplex data storage with query execution without affecting performance.
Cool. So yeah, I guess you're very pessimistic at the start of the project, and progress in research is very non-linear, right? There's a lot of ups and downs. So kind of from the conception of the initial idea for Scabbard to the publication, I guess how long did that take, and what were the things along that journey that you tried, that failed, that maybe other people in this area could benefit from knowing?
Okay, so I didn't have any experience in fault-tolerant before, so I had to learn everything the hard way. And I was very naive at the beginning on how you can perform, for example, checkpoints. So in our first submission that got rejected, of course, I was trying to have a more general model when you can checkpoint different data streams and different operators without synchronization, which at the time I thought it was very cool. But it was very hard to reason about because when you were recovering, you would end up in scenarios where your state was not consistent. So you would have to replay the whole thing from scratch. So that was an issue that I found. And also I had many issues with the implementation. So I thought that I was very smart and I could do very fast, like lock-free programming, and they use like very smart data structures for doing checkpoints while doing processing at the same time in shared memory data structures. And yeah, I failed miserably. So yeah, my code was full of concurrency bugs and I had to go back to using locks and doing like the simple things. And in the end of the day, this was just like premature optimization. I tend to do this. So I try to optimize for things that are not important.
Right. Yeah.
And yeah, I shouldn't do this.
Okay, cool. I know you've since submitted your thesis and have left academia, but what's the future, the plan for future research with Scabbard? I guess is your group going to plan on taking the project forward, or what's the future goals for it?
So I mean, we didn't go far with these ideas, but we wanted to test to do different things. So the first was multi-tenancy in stream processing. So because you have these long-running applications, you may want to have multiple users in a single server, and we want to see how we can manage all these limited resources that you have when you have multiple users. So now it becomes much more challenging to deal with the CPUs, the disk, the network bandwidth. So yeah, that was one of the directions. And the second one was, okay, so now we have a system that can persist data streams and state fast, but there's no way that you can do queries on both historical and streaming data. So you cannot really do run queries on you cannot combine these two together, right? So we would like to have an approach for out-of-core processing, where you can spill things to disk, you can have indexing, but designed in a different way compared to like classical relational systems, right? So that you could still have these low latency requirements fulfilled in a way.
Yeah, so obviously over the course of your PhD, you worked on numerous topics. Can you maybe tell the listeners about your other research and things you worked on during your time?
Yeah, so I mean, we mainly focused on single node, and when we before I tried to go distributed my time. I did. We started from optimizing specific operators with simple instructions, how we can like run very efficiently from a single core. Then we moved to multi-core execution with multiple sockets, and we try to bring ideas from relational database like code generation to stream processing, which was really interesting. And finally, we try to make a single node system at the same time fault tolerant with the assumptions from earlier. So we're trying to fully utilize all the resources you can find in a single node, trying to make the most out of it.
Cool. And I don't know if I sent you this question, so apologies if it catches you off guard. But I was walking down the street the other day and thought, this would be an interesting question. How did you go about during your PhD, and in general, I guess even in your day job today, it's very research orientated. How do you approach idea generation, and then how do you then choose what ideas to work on and select projects that are worthwhile pursuing? What's your process for that, I guess is what I'm asking.
Yeah, I think I don't have a very good process. So I read a lot of papers, and so as I said before, stream processing is not that mature. So usually I try to kind of not still borrow ideas, let's say, from relational database or other like processing paradigms. And I try to adapt these ideas from the papers that I read to a real-time analytics world, like a streaming world. And I was also, I had like a lot of ideas, most of them not very smart, but I was also kind of lucky because I had two supervisors, and they were coming from two different worlds. So when I was pitching ideas to them, they also helped me steer and pick what I was going to do. So as I mentioned earlier, I don't think we did anything. I mean, there was novelty, but I don't think that we did something that was unexpected. So yes, as I said, we tried to implement code generation in stream processing. So I mean, it was interesting, but this was, for example, a project that came from relational databases.
Okay. What do you think is the biggest challenge in stream processing today?
Yeah, I think that the project that I mentioned earlier about unifying streaming with historical data with a way that you can provide low latency results, I think this is one of the biggest challenges. Because you have to deal with novel data structures for indexing, novel ways of, and even protocols of how you buffer your data, because you don't have like let's say the relational database, a pattern of how you do the access, right? So you have to think of what data is going to be your hot data, your cold data, and how you evict data, for example, from your buffer manager. So I think that this unification is a very interesting problem.
Cool. So last question now. What's the one key thing you want the listeners to take away from this episode and your research?
I found this quote in Frank McSherry's slides. It goes like this. So it says, you can only have a second computer once you've shown you know how to use your first one. So I think that this is what we're trying to show with our projects, that you have to somehow think out of the box and try to redesign systems so that you achieve resource efficiency and you exploit the hardware trends that you can find right now. So that's it, I guess.
Brilliant, and that's a wrap. Let's end it there. Thanks so much, George, for coming on the podcast. If the listener is interested to know more about George's work, then I'll put all the links to all the relevant materials in the show notes. And we will see you next time for some more awesome computer science research.